Okay, so let's start from last session, page 52. So now we're going to talk about Nakagami. Uh, so both the Rayleigh distribution and Rice distribution are frequently used to describe the statistical fluctuation of signals from fading channel. So as you see, the oftentimes when we see in the papers about the H or H, this notation H representing the channel, it's very often described by a couple of those random variables. The most common ones are Rayleigh, Rice, and Nakagami. Those are the common ones describing the statistical property of the channel. The channel models will be considered later. Then another distribution that is frequently used to characterize the statistics of signals through multi-phase channel is Nakagami distribution. The PDF for this distribution is given by Nakagami in the 60s. Okay, so we have P of X equal to uh, if x larger than 0 is equal to this, or otherwise it will be 0. And what happens is you have 2 divided by gamma of that is the gamma function we have, and parentheses divided by omega, is capital omega, and we will define it later. So to the x squared 2 minus 1 exponent minus x squared divided by omega, and then omega is defined as this, that is the aspect of x squared, and the parameter is defined as a ratio of moments called the fading figure. This is like S factor before in Riccian there's a Riccian factor, and here we have a fading factor that is defined by omega squared divided by e of x minus omega squared. Okay, and a normalized version is obtained by defining another random variable y equal to x divided by square root of omega. The nth moment of x is given by, but for this normalized version, of course, it has different properties, which uh, we may be able to talk about it in problems or practices, but uh, here we still focus on the regular version. That the nth moment of the regular version is backed of xn equal to gamma m plus n divided by 2 and divided by gamma m. As you can see, we use gamma function a lot. And then omega divided by m, n divided by 2. Okay, so this is just a expression. The mean and variance for this random variable are given by this. Yeah, aspect of x equal to gamma of m plus 1 over 2 divided by gamma m, parentheses gamma divided by m, 1 half to the 1 half to the 1 half. And then variance of x equal to omega parentheses 1 minus 1 over m parentheses gamma m plus 1 half over gamma m to the order 2. Okay, so the first and second order statistics are always of our interest, and in fact they are most critical ones. So let's not forget about uh, expectation of the x and then variance of x. That's the most critical ones. And as we can see, this is a fading figure. And in fact, what is the fading figure? If we see that fading figure sort of representing, if you see this, sort of representing how concentrated the distribution is, right? How much concentrated the distribution is. So as you can see, if the numerator is large, what does it mean? If the numerator is large, meaning that it's very it's very widespread, right? It's very widespread, and that you're going to have small fading figure. If the numerator is smaller, then you have a large fading figure, and it's going to be more concentrated. So you see that m equal to 3 is very much concentrated, right? You see that distribution is concentrated around this area, right? This is a Nakagami distribution in omega equal to 1. Is a fading figure. And let's see, if you have equal to 2, then you're going to have concentrated a bit, but not as much as 3. And uh, all the way down, if you take a look at this, wow, it's like it distributed more widespread, distributed, right? More widespread. So, so we are having uh, a bit of the what? A bit of the distribution, the shape of the distribution. Uh, and you see that with the increase of you see that concentration of probability density seems to be spreading out with the increase of the fading factor. Okay, so that is the Nakagami. And the next thing is log normal. Log normal. So suppose that a random variable y is normally distributed with mean. A random variable y is normally distributed with mean and variance is sigma squared. Let us find a new random variable x that is related to y through the transformation y equal to natural log, that Ln representing natural log x. Or if you rewrite it into a different format, it will be x equal to exponent to the y. Then the PD of x is p of x equal to this, and for x larger than 0, it is the 1 over square root of 2 pi sigma square x exponent minus ln x minus m squared divided by 2 sigma squared, something like that. And otherwise, meaning x smaller than 0 is 0. So for this random variable, its spec of x is equal to em plus sigma squared over 2. So that's the first order statistics. And then the second order statistics is variance of x equal to is backed up to plus sigma square parenthesis to the sigma square minus 1. So that is the variance and this is expectation. Okay. So the log normal distribution is suitable for modeling the effect of shadowing of the signal due to large obstructions such as tall buildings in mobile communications. Okay, so The next thing is the jointly Gaussian random variable. So we are going to talk about multiple Gaussian and jointly they are Gaussian. So n by 1 column random vector with components xi is called the Gaussian vector, as its components are called jointly Gaussian random variables. So recall that when we talk about uh, vector, we are imagining a column vector with elements inside, right? One after one, one after one, and we have a column vector. So we are supposed to think and imagine we have a random vector with this column vector and all its elements is a random variable. And then of course in this case it's even more well defined by Gaussian. Okay, so let's think about this way. So by the way, log normal random variable. If we take a look, we have a different values of and you see distributions. And go back a little bit. If we look at the log normal, it's defined for positive domain. So we have this positive domain random variable log normal. Okay, then jointly Gaussian. Uh, we have multivariate Gaussian random variables. If a joint PDF of xi can be written this way, and the fact is, uh, if it's a joint PDF, uh, a joint Gaussian, if it's a joint Gaussian, it has to be able to be written in this way. And we look at that x, think about a column vector. Okay, and then it's 1 over 2 pi n divided by 2 and determinant of a covariance matrix C over 2 to the n divided by 2 and exponent to the minus 1 over 2 x minus m transpose C dot teach meaning transpose C minus 1 x minus m, where m and c are the mean vector and covariance matrix of x, and we can explicitly write it out by m equal to expect of x, c is equal to expect of x minus m transpose. So from this definition, it's clear that Cij is a covariance of xi and xj, okay, and C is a symmetric matrix. From elementary probability, it's also well known that C is a non-negative definite. It's just a little bit away from positive positive definite. So if we take a look, that C is what? It's n. When it comes to matches, I always like to think about the dimensions first. So it's n by n. C. So if we look at this is n by 1. Right? If we clarify the dimensions, the problems will be clear. Will be clear when we see it. So it's n by n, and you have this diagonal elements covariance matrix. Okay? And then what is this? Think about it. What is this first element? First element is the variance of this first variable. right? Second element is the variance of the second element, so on and so forth. And how about Cij? For example, this off diagonal element, that is according to its subscript ij, it's the I with respect to j. So let's say C2, 3. What does it mean? It's a covariance of the second one, and the third. That is, you take the covariance of the second and the third. It's second with respect to the third. Then you get C2, 3. You get C2, 3. So that is the structure of the covariance matrix. Okay. And in the special case of n equal to 2, we have something very clear. That is the m equal to m1, m2, and C, as you see, the first element is sigma 1 square, sigma 2 square, and then log sigma 1, sigma 2, log sigma 1, sigma 2. Okay, so it's just as what I say here, and if you write it out for n equal to 2, then you get something like this. And then rho is the covariance of x1 and x2 divided by sigma 1, sigma 2. That is the correlation coefficient. So here, up to this point, we talk about covariance and correlation, right? So there are two vocabularies, terminology. The one is the variance, and the one is the correlation. And the difference is that uh, they are related. They are related, and variance divided by standard deviation, it becomes correlation. So it's sort of correlation is a normalized version of variance. Okay, so that's the way we can think about this. And we have this correlation coefficient of the two random variable. And in this case, the PDF reduces to px1, x2, 1. I believe it's easy that we can write this out. The PDF reduces to p of x1, x2 equal to 1 divided by 2 pi sigma 1, sigma 2 square root of 1 minus rho square exponent to this. And if we recall previous case where we have no correlation, then what happens is you have rho equal to 0, and then it reduces to the typical Gaussian that we are used to, right? 1 divided by 2 pi sigma square and something like that without this law, because law is equal to 0. That's the IID case. But if we have correlations, then the law has to be put into play in the equations. So m1, m2, sigma 1, sigma 2 are means and variance of the two random variable, and rho is the correlation coefficient. And note that in the special case when rho is equal to 0, the two random variables are uncorrelated, and we have px1, x2 equal to normal distribution, that's a regular Gaussian, multiplied by a regular Gaussian. So this means that the two random variables are independent, and therefore for this case independence and uncorrelatedness are equivalent. This property is true for general joint Gaussian random variable. So what it means is uncorrelated, meaning independence. Independence and uncorrelatedness are equivalent. This is general true. And I have to point out that this is true only for Gaussian. If you have a random variable that is not Gaussian, then this may not be true. Okay, so Gaussian is something that is well behaved. Well behaved, meaning that we have uncorrelatedness equivalent to independence. But if you want to argue that independence equal to uncorrelated for other kinds of random variables, you actually have to prove it. It's not trivial. In most cases, this is not true. Okay, so another important property of jointly Gaussian is the linear combination of Gaussian are also Gaussian. So if you make a summation for Gaussian, the outcome will be Gaussian. So that to put it eloquently, verbally speaking, summation of Gaussian is Gaussian. Okay. In other words, if x is a Gaussian vector, then the random vector y equal to a multiplied by x. Notice that this is a vector version multiplication. It's not scalar version, where the invertible matrix represents a linear transformation. It's also Gaussian, whose mean and covariance matrices are given by this and this. Okay, so uh, you have mean multiplied by A, you have your covariance multiplied by A and A transpose. Because this is a second order statistics, so you have two coefficients. You have a second order uh, A in it, that is the A CX AT. Okay, so that uh, is the second order statistic. So in summary, the joint Gaussian has the following property. For jointly Gaussian, uncorrelated is independence. Linear combination of Gaussian is Gaussian. And the random variable in any subset of jointly Gaussian are jointly Gaussian. Any subset of random variable condition on random variables in any other subset is also jointly Gaussian. Okay, so yeah, I think we go up to here and take a break and come back later.